So the first thing we want to talk about when we are studying fluids is, what is a fluid? So normally, I ask my students to define a fluid in their own words. So I get answers like, well, fluid can be water, it can be air, it can be oil. So I get a lot of examples of what fluids are. But we can't just really list all the fluids, right? We need to know what fluids are. So we need to know, what does water, oil, and air have in common? The best way to define a fluid is not necessarily by its composition, but rather by its properties. If we were to apply a stress or a force to a fluid, the question would be, how would that fluid react when compared to other substances? So what other substances are we looking at? Anything that's not a fluid, you might say, is a solid. So if we look at a solid, we have our solid here. It can be anything you want to be. It can be concrete, it can be wood, just some solid. And if we were to apply a shear stress to this solid, what would happen? Some students say, well, depending on the magnitude of the shear stress, it can deform or not deform. Which means that there is a certain magnitude of shear stress that we need to reach in order for the solid to deform. So let's say we did reach that magnitude. What happens to the solid? Well, it deforms. But the question is, how long will that solid keep deforming? There is a point at which the solid will not go back to its original state. But there's also a point where the solid will go back to its original state. So when solids deform, we need to look at their yield point. But now let's look at fluids. Suppose I have my fluid substance here. And suppose that I were to apply a shear stress to that fluid. Now, if I ask you what would happen to this fluid, you would also reply, well, it also deforms. But now, the questions that we want to ask ourselves are, will this fluid require a minimum shear stress to deform? So I want you to think about that. Think about water, or think about a gas, something like air. Would you need a minimum, a small amount of shear stress in order to deform that fluid? The answer is no. The answer is that no matter how small your shear stress is, it will always cause your fluid to deform. Now the second question is, how long can this fluid deform? And I'm just going to give you the answer. The fluid will continue to deform as long as you're applying the shear stress. So, different from solids, fluids don't require a minimum shear stress to deform, and will continue to deform as long as you're applying your shear stress. So we can use those two terms to define our fluid. We can say that a fluid is a substance that deforms but we want to be careful here because solids deform too. So we can't just say this fluid is a substance that deforms. We say that a fluid is a substance that deforms continuously. And that's a key word there. Solids and fluids both deform under shear stress, but fluids will deform continuously. Now at this point I ask, is this definition enough? And I get a lot of mixed answers. Some students say yes, some students say no. So I want to look back at the solid and the fluid. We know that a fluid will continue to deform, but that wasn't the only thing that made a fluid different from a solid. We also know that it doesn't matter how small your shear stress is, as long as you apply it, the fluid will deform. Which means that we don't need a shear stress to be of a certain magnitude to cause the fluid to deform. So our definition will be a substance that deforms continuously under a shear stress, but we can say under any shear stress, or a shear stress of any magnitude. Now, all the answers that I normally get for fluids are pretty much correct. Water is a fluid, yes. Air is a fluid, yes. I've received answers such as a fluid is something that flows. Well, yes, it is. However, I like this definition because this definition really stresses the importance of this class. Because this class is called fluid mechanics. And in this class, we're going to study fluids, but more than that, we're going to study how fluids react to forces and stresses acting on them. So what is a fluid? A fluid is a substance that deforms continuously under any shear stress. Now, normally in my previous classes, I talked about some applications of fluid mechanics, and we would go over some industries and how they use fluid mechanics. So we would say civil engineers use fluid mechanics for stormwater management. Mechanical engineers use fluid mechanics for HVAC design. Aerospace engineers use fluid mechanics for propulsion. However, today I don't want to talk about those applications. You can read them in your lecture notes. Instead, I want to talk about why we study fluid mechanics. Not just what we can do with it, but why we like to study fluid mechanics. The question I like to pose for my students is, why do we study fluids? Why do we care about fluids? Why do we dedicate an entire semester and sometimes even more to the study of fluids? And the answer is, well, fluids are all around us. Right now, we are all surrounded by a fluid, and that fluid is air. Every day, we drink water, another fluid. In fact, our bodies are made of water, another fluid. So fluids govern every single thing that we do. And that's why I love this field. That's why I think this is such an interesting field to study. There was a good example that I heard in my lecture today. When we look at the transportation of your food, from the moment you eat it to the moment it returns to the nearest water body, that gives us a long, long path of fluid mechanics concepts. Because we have biological processes where you digest your food, where you excrete it. We have engineered conduits. Those are your wastewater systems where fluids travel. We have your wastewater treatment plants, which for the most part consist of chemical processes. And then, when wastewater effluent returns to the ocean or to the nearest water body, we then have more fluid mechanics, because we have water mixing with the natural water body. So I like that analogy. It's a little bit gross, but it is a good analogy of how different fields, biology, engineering, chemistry, hydraulics, how different fields interact with fluids. So we've talked about what fluids are. We've talked about why we study fluids. Let's talk a little bit about the history of fluids. Now, there's a couple of important points that I provide in my lecture notes. However, those points aren't really representative of fluid mechanics history as a whole. I can't really go over an entire course in the history of fluid mechanics, but I do recommend that you read the lecture notes and that you study a little bit more. There's a book that I like called A History and Philosophy of Fluid Mechanics by G.A. Toccati. One important thing to note about fluid mechanics in terms of its history is that fluid mechanics principles have been in application for a long time. If we go back 3,000 years in time, we'll see that the Egyptians had already discovered that a smaller cross-section in a river resulted in a faster velocity. We'll see ancient civilizations using fluid mechanics principles for the purposes of navigation and irrigation. Fast forward a little bit to the time of Archimedes. We'll see the concepts of buoyancy being explained. We'll see the Romans designing their aqueducts to provide water supply to their city. Fast forward a little bit more to the time of Leo da Vinci. We'll see fluids concepts being applied to design hydraulic structures. It wasn't until the development of calculus when fluid mechanics became a strongly mathematical field. Because through calculus, we had new doors with which to study these fluids. Now, there was a time where fluid mechanics theory and fluid mechanics application functioned as two separate fields, which some books call the fields of hydrodynamics for the mathematics part and the field of hydraulics for the engineered or practical part. The reason these two fields developed separately was because there wasn't a way to reconcile mathematical theory with the engineering applications and observations. So while hydraulic engineers developed empirical equations, mathematicians developed hydrodynamic theoretical equations. However, that all changed with the derivation of the Navier-Stokes equations, which we will talk about later in this class. What I'm trying to get at here is that fluid mechanics is a continuously developing field. Even now, we are still advancing the fields of fluid mechanics. We use experimental methods to study fluids. We use analytical or theoretical methods to study fluids. But now we can also use computational methods and numerical methods to study fluids. So probably by the time we end this semester, there will be more advances in the field that we can talk about. And that's why I like this field. It's not a boring field. It's not a stale field. It is continuously being developed. And there's a lot of problems in it that are still unsolved, that maybe one day one of you will solve. So that's it for an introduction to the study of fluids. In the next lecture, we're going to talk about dimensions, units, physical quantities, and some of the prerequisites of what we need to know in order to study fluids. So in the first lecture, we talked about what fluids are and why we study them. Today, we're going to talk about how we can study fluids. Specifically, we're going to look at some of the prerequisites, the things that we need to know and understand in order to study fluids. Now, any field that requires some sort of measurement requires us to know what dimensions and units are. Now, we all know what dimensions and units are. We've all done unit conversions before. However, I do want us to understand where these units are coming from and how they relate to each other and how they relate to the world around us. So I want to first start by talking about physical quantities. Physical quantities are those things that we use to quantify the world around us. Physical quantities can be quantified, or you can say measured, using dimensions. Now, when you hear the word dimension, you may think about the three dimensions of space that we are living in, dimension of time. But there are more dimensions than that. Regardless of how many dimensions you can think of, we typically tend to lump all of these or simplify them into 9 fundamental dimensions. Now, we're not going to go through all of the fundamental dimensions in this class. However, we will focus on 5 fundamental dimensions for this class. Now, when I ask students to list what they think would be the fundamental dimensions, I always hear length, which is a good one. I always hear about mass. And I always hear about time. But those aren't the only fundamental dimensions. When we're looking at the study of fluid mechanics, we also want to think about two more fundamental dimensions: temperature and angle, specifically plane angle. Now, in this introductory undergraduate level course, we will focus on using 5 fundamental dimensions. There are 4 others that we use in physics, but for this class, let's focus on length, mass, time, temperature, and plane angle. You can get more information on fundamental dimensions on the lecture notes. But as long as we understand that length, mass, time, temperature, and plane angle are fundamental dimensions, then we will be able to use them. Now, what separates or distinguishes a fundamental dimension from a dimension? The way we want to define fundamental dimensions is as those dimensions that cannot be broken down or expressed in terms of other dimensions. For example, if we think of an area, how can we express an area in terms of one or more of these fundamental dimensions? I think you all know the answer for that. We can express an area as 2 dimensions of length. Let's try again. What if we think about density? Now, when I ask students who just finished a physics course, what is density? I always get the same answer: mass over volume. We can define it as mass over volume if we want. But volume isn't really a fundamental dimension. Mass is, so we're good on the numerator. But how can we express volume in terms of one or more of these fundamental dimensions? Students normally define it as 3 dimensions of length. So if we want to express a density measurement in terms of its fundamental dimensions, we would express it as mass over 3 dimensions of length. So we have dimensions, such as areas and volumes, but then we have fundamental dimensions. Now, depending on how or what system of units you decide to use, these dimensions may change. When you think about mass, you think about kilograms. However, we also see kilograms as a way to measure our weight. Mass and weight aren't necessarily the same thing. Mass is a mass, weight is a force. So some systems prefer to use force as the fundamental dimension and mass as a derived dimension. And we're going to talk about that in a second. I mentioned the word kilogram, but kilogram isn't really a dimension. It is not a fundamental dimension. So what is it? We know that kilograms are units. So units are standardized ways, standardized measurements that we use to quantify these fundamental dimensions. Now, I don't have to go too deep into what units are, but I will say that in this class, because we are teaching it in the United States, we will focus on 2 unit systems. The US customary system, which is based on English units, and the international system, which is based on metric units. Now, you already know this, but just to give you a refresh, in the US customary system, which we will almost always abbreviate as either US or EN for English, the units for length are going to be feet, the standard units. Are there other ways to measure feet, to measure length in the US customary system? There are. We have inches, we have yards. Is yards a US? Okay. But the standard way would be to use feet. In the international system, which we abbreviate as SI, because it's a French word, the standard unit measurement for length is the meter. Now, normally in class, I ask about the others. For mass, we know that the international unit would be kilograms. But I always hear the word pound mass for mass. However, here's where the confusion between the US customary system and other systems that use English units kind of comes into play. You see, in English units, mass is a derived unit. And so we don't use pound mass. Instead, we use slug. Now, if you've used slugs before, then that's good. If you haven't, don't be scared. This is simply a unit that we use to measure mass, just like feet are units that we use to measure length. When it comes to time, there is no difference. We use seconds for both English and metric units. There was a very sad attempt to standardize time in base 10 numbers, right? But that didn't work out. So time, we still measure it in seconds for both unit systems. Now, normally at this point in class, there's always a fun little debate about which system is better, US or metric. Most people in academia and international are going to say metric system. Most people that are not in academia are going to say the US system. Look, the reality is that while the metric system makes more sense from a mathematical side and it's easier to grasp mathematically, it is not as intuitive as the English system. And you can say that. I grew up with both systems, US and metric. And we use them in our day-to-day, both of them, sometimes at the same time, within the same sentence. In fact, if you look at one of the plans that I've designed when I was working in Puerto Rico, you'll notice that the entire plan is written in metric units, but we always talk about it in English units. So it's kind of weird. But the reality is that growing up with both systems, giving both of them the same priority, I can really say that the US system is more intuitive, whereas the metric system is more mathematically logical. When it comes to temperature, we get to a bit of a slump. Because some students will say that the degree Fahrenheit is the standard unit for the US system and that the degree Celsius is the standard unit for the metric system. But both of these answers are not quite correct. Yes, degree Fahrenheit is an English unit. Yes, degree Celsius is a metric unit, but they're not the ones that we use for temperature. Instead, we're going to use the degree Rankine for the US system, and we're going to use the Kelvin for the metric system. And we're going to talk a little bit about why we use those two different units in a second. What do you think is the unit for angle? I'm going to hear a lot of people say degrees. But in standard terms, we're going to want to use radians. And the interesting thing about radians is that when we're doing our dimensional analysis, when we are plugging and chugging our equations and combining units, radians somehow seem to disappear. When we look at something like frequency, we express frequency as 1/2. We don't really say radians per second. So radians is an interesting one. We're going to talk about that later. There are different ways that we can express values in the metric system. Particularly when we're dealing with larger values or very small values, there are two techniques that we use. We can either use SI prefixes, which attach a prefix to the unit that represents a power of 10. For example, if I want to say 1,000 meters, I could attach a prefix to this meter unit that turns it into 1,000 meters. In this case, my prefix will be kilo. So instead of saying 1,000 meters, I can say 1 kilometer. I can do the same for larger numbers. We can look at 1 million meters. We can express a million meters as 1 megameter. These prefixes are not something new to you. You've already used them before. Now, frankly, I'm going to try to shy away from them as much as I can. And instead of using prefixes, I'm going to try to use scientific notation. Now, what scientific notation does is express large numbers as products of a number times a multiple of 10, a power of 10, sorry. So a large number such as 1 million can be expressed in scientific notation as 1 times 10 to the power of 6. Now, normally when we're using scientific notation, we want to make sure that we can agree on the number of significant units. Now, I don't have to explain these things because you've already done them before. However, I do want to make sure that we understand the different ways that we can use to express numbers. So sometimes I give out a quiz that has a long answer, and the answer is returned to me like this. I'm not going to say meters, let's say newtons. And whether this answer is correct or not is not really a problem. It is to me, but the issue is that this could be expressed using one of these two methods. So, I would just like to advise you to try to use SI prefixes or scientific notation in order to give your answers the correct degree of precision. When we're looking at different equations in fluid mechanics, when we're looking at different problems, we always want to make sure, or for the most part, we want to make sure that our equations are dimensionally homogeneous. Now, this may be a new word for some of you. We have covered it in statics before, but if this is a new term for you, then don't worry. It sounds worse than what it really is. For an equation to be dimensionally homogeneous, all of the terms in the equation have to have the same dimensions. That's what allows us to perform mathematical operations with that equation. Now, that's a bit of a long definition. Let's just express it. So, in a dimensionally homogeneous equation, if A is a length, then B has to be a length. And C also has to be a length in order for it to count or qualify as a dimensionally homogeneous equation. Now, we're getting to a point where too much explanation isn't really all that helpful without a real example. So let's look at an example of fluid mechanics. Here's an equation that we are going to work with a lot this semester, particularly after the first exam. This equation is a very famous equation in fluid mechanics called the Bernoulli equation. And the Bernoulli equation says that the sum of the pressure term, the kinetic term, and the potential term at 2 points along a streamline for an ideal fluid is a constant. Now, here's the Bernoulli equation. You may have seen some of these terms. You may have not seen other terms. But just with what you know from physics, the question would be, what are the dimensions of the constant? So think about it. Just with me giving you this information, and with whatever you've learned from physics, can you tell me the dimensions of this constant? You may be confused by this gamma term here. But do you really need to know what pressure over gamma is in order to find the constant? Or is it enough if you know what one of these other two terms is? So when we talk about dimensional homogeneity, in order for this equation to be dimensionally homogeneous, all terms in the equation have to have the same dimensions. So if I'm already telling you this is a dimensionally homogeneous equation, then what are the dimensions of the constant? Well, let's start with the velocity, because that's something that we're already familiar with. The velocity term is velocity squared over 2 times gravitational acceleration. Let's try to express this in fundamental dimensions. What are the dimensions of velocity? We know their length and time. And are those fundamental dimensions? Yes. So we have length over time. But we want to be careful because this velocity term is squared, which means that we won't just have length over time, we will have a length squared divided by a time squared. The dimensions are 2 are just 1, no dimensions. What are the dimensions of gravitational acceleration? Now you know that it's an acceleration. And if you forgot what the dimensions of acceleration are, then just think of the units. What's gravitational acceleration? You will say 9.81 meters per second squared. Okay, so look at meters per second squared. What is meters? A length. And what is second? A time. So the dimensions of gravitational acceleration are going to be length over time squared. If we want to solve this equation, what does that give us? Notice that the time squared cancels with the time squared, and one of the lengths in the numerator will cancel out with the length in the denominator. And that results in dimensions of length. So now if I ask you, what are the dimensions of the constant in the Bernoulli equation? What will you say? Length. We didn't have to figure out that z was a length. We didn't have to figure out what this gamma term is. However, now that we know that the dimensions of all the terms in the Bernoulli equation are length, at least the way we express it, then you do have everything you need to calculate the dimensions of this gamma term, which we will talk about next week. When we study fluids, we want to focus on all the forces that are interacting with the fluid. Now, those forces can include impact forces and can also include body forces. There's one body force that's very common in fluid mechanics and that we will almost always consider. And as you may have already guessed, that is the force of gravity. Now, everybody knows what gravitational acceleration is. And if I were to ask you to tell me the value, or at least a nominal value, of gravitational acceleration, you would tell me it's 9.81 meters per second squared. So if I say, what is gravity? You may define it as just 9.81 meters per second squared, or you may define it as 32.2 feet per second squared, depending on your unit system. However, when we're studying fluids, we need to understand that not all of our fluid systems are going to move in one dimension, which means that gravity may not always act in the direction of flow. In fact, for the most part, if you look at natural systems such as rivers, gravity will drive the flow, but flow will not be moving downward. It's going to be moving somewhat horizontally. So, when we're looking at gravity, we cannot treat it as just a scalar. We need to remember that gravitational acceleration is a vector. So gravitational acceleration is a vector with a magnitude of 9.81 meters per second squared. If I use my I, J, K standard for my X, Y, and Z axis, then gravitational acceleration will be equal to negative 9.81 in the unit K direction. I want to make sure we get that through our heads. Let's try to treat gravity as a vector, because our fluids will most likely not always move in the direction of gravity. They will most likely not always move in the direction normal to gravitational acceleration. So we will have to consider gravity, but we may need to also consider the direction of flow. Now we're treating gravity here as if it were a constant. But that's not entirely true. In fact, gravity varies with elevation. We already know that. I'm going to refresh Newton's law of gravitation. If you remember, Newton's law of gravitation stated that the force of attraction between two objects was equal to the universal gravitational constant times the product of the two masses divided by the square of the distance between the two objects. Specifically, the distance between the center of mass of the objects. From this law of gravitation, we can come up with a nominal value of 9.81 or 9.82 depending on how you do your math. However, notice this. The weight of an object is defined as mass times gravitational acceleration, where mass would just be the mass of the object, and gravitational acceleration should represent the universal gravitational constant, the mass of the Earth, and the distance between the Earth and the object, which we typically take as the radius of the Earth, assuming that the Earth would be a sphere. But notice that the further you are from the center of the Earth, the larger this value is, the smaller gravitational forces on you. Which means that we can't really treat gravity as a constant. You can treat gravity as a field, but not a constant. However, this is an engineering mechanics class, right? It's fluid mechanics, but for engineering students. And in engineering applications, at least the applications that we're going to learn in this class, the variation in gravity between different points on Earth is going to be so small that we can actually neglect it in favor of a 9.81 constant. So why am I telling you all this if we're still going to use 9.81? Because I don't want you to go through life assuming that it is a constant. I want you to understand where our assumptions come from. I want you to understand that they're not just givens. If we know how gravitational acceleration works, we know how weight works, and weight will be an important body force to consider when we're deriving our fluid mechanics equations. In this class, we're not going to deal with the effects of electric and magnetic fields on fluids, but we will see the effects of gravitational fields on fluids. So make sure you memorize this equation. Weight can be calculated by just mass times gravity. This will be the scalar form, but we can also write it in vector form. Okay? So earlier in class, when we talked about temperature, I mentioned that we were going to talk about why we have different units for temperature. So there are different scales by which we measure some properties. Those are known as absolute and relative scales. And there are two fluid properties that we will measure using one or two or a combination of absolute and relative scales. One such property is pressure. Now, when I ask my students to define pressure for me, they will normally say, well, pressure equals force over area. That is true to a certain point. If we were to look at a force distributed over an area, and if we were to focus on a small element with area delta A, then as that area delta A tends to 0, then we can define the pressure as the differential force over that differential area. However, if we assume that a pressure is uniformly distributed over an area, then this pressure becomes simply force over area. Again, we can use this definition, but I want you to understand where it comes from. We say that pressure acts over an entire area. So you will hear me say things like pressure at a point, and that's also a measurement we make. But when we look at pressure, we're going to try to always understand it in terms of acting over an area. Now, right now, for those of you that are sitting down, or for everyone in this room, what forces are we experiencing? Everyone's going to say gravity. But there is one force that we're experiencing. Oh, yeah, normal force. But there is one force that we're experiencing that students typically tend to neglect, and that is pressure. We're all experiencing some sort of pressure that comes from the air above us. That pressure is called atmospheric pressure. Atmospheric pressure depends on our location because it depends on the amount of air that we have above us. So atmospheric pressure varies with elevation. And for standard engineering conditions, our objects will be experiencing atmospheric pressure. Now we can define a second type of pressure as gauge pressure. And gauge pressure would be any value above or below the atmospheric pressure. In other words, this desk is experiencing atmospheric pressure. But if I were to apply an additional pressure to the desk, it's experiencing atmospheric pressure plus the pressure that I'm applying to it. That pressure that's different from the atmospheric pressure is what we call gauge pressure. So now if I were to ask you, when I am doing this to the desk, what is the total pressure that the desk is experiencing? Students will say, well, the total pressure will be equal to the sum of atmospheric pressure plus gauge pressure. Now this is a good definition because it allows us to express pressures in terms or in relation to atmospheric pressure. You see, when we're dealing with engineering conditions, the atmospheric pressure doesn't really vary between what's on my head and what the pressure on the head of a student that's sitting down. Because that variation is not really that big, and because in the study of fluid mechanics we're going to look at pressure differences instead of just absolute pressures, then it is easy to express pressure in terms of only its gauge pressure. For example, when you are filling the tires in your car, and you got to fill the tires to a pressure of 35 psi, pounds per square inch, is that the total pressure on your tires? The answer is no. The total pressure on your tires will be equal to atmospheric pressure plus those 35 psi. So unless otherwise specified in this class, we will treat gauge pressure as the measurement for pressure because we will assume that the objects that we are studying are experiencing already an atmospheric pressure. So in terms of gauge pressure, what would atmospheric pressure be equal to? In other words, if we want to study an object using gauge pressures and want to look at the effects of atmospheric pressure on that object, we would say that the atmospheric pressure is equal to 0. Now this can be a little bit confusing sometimes because students will say, well, but there's still a pressure. How can it be equal to 0? Well, because when we are studying pressures, instead of studying the absolute or total pressure, we can focus on studying the gauge or relative pressure. So the relative pressure measurement that we will use in this course will be gauge pressure. So there are two scales for pressure. We have an absolute scale, which considers atmospheric pressure and gauge pressure, and we have a relative scale, which considers only gauge pressure. So you'll see me saying pressure at the surface of a fluid is 0. That doesn't mean that there is no pressure acting on the fluid. What that means is that we will be studying the fluid using gauge terms. Now this is something that we can do in engineering applications where there is little to no variation in atmospheric pressure. But we cannot do this when we're looking at pressure differentials between objects on Earth and objects outside an Earth orbit. So we've got to be very careful and selective with when and how we use our relative and our absolute measurements. There's another absolute and relative scale that we use in fluids. We talked about pressure. Now we can look at temperature. So we already talked about how the units of temperature are typically said to be degrees Celsius, degree Fahrenheit, but the standard units are actually degree Rankine and Kelvin. And the thing is, what's the difference between these? To answer this, I would first pose a question, right? So what is temperature? When I ask this question, I get results like, well, temperature is a measure of how hot or how cold something is. Or temperature is a measure of how much energy can be transferred from one point to the other. And frankly, I'm not a thermodynamics person, but I would say temperature is something related to a measure of some type of energy, right? Maybe like a measure of thermal energy or kinetic energy, or a measure of specific heat, maybe a measure of the vibration of molecules. However way you want to define temperature, the units of Rankine, degree Rankine, and Kelvin measure what we call absolute temperature. In other words, they measure the vibration of molecules. Now, because they measure vibration of molecules, there is a term where these numbers are zero. Now, we're not going to get into the quantum physics of it, okay? But we will say that these numbers cannot be negative because you're measuring vibration. You can measure no vibration, that's zero, but there is no negative vibration. So these numbers will be positive. But where does Fahrenheit and Celsius come into play? So Fahrenheit and Celsius are what we call relative temperatures or relative scales of temperature, because Fahrenheit and Celsius are based on the freezing and boiling points of water. So for degrees Celsius, we can set the freezing point of water as our 0 and the boiling point of water as our 100 degree. And then everything else in between, we just accommodated. Likewise, with degrees Fahrenheit, we can set the freezing point of water as 32 degrees, and we can set the boiling point of water as 212 degrees. And then everything else in between. There are unit conversions between Celsius and Kelvin and Fahrenheit and Rankine. And you can look up those unit conversions. In this class, for the most part, I'm going to try to use relative scales, such as gauge pressures, degrees Fahrenheit and degrees Celsius. But there are some applications, specifically thermodynamic applications, where we cannot use relative scales for pressure nor temperature. And in those cases, we will look at absolute pressures, and we will also look at absolute temperature scales. But you will see those cases identified. So I want you to have an idea of what we're talking about when we say relative, when we say absolute. I've been mentioning a term several times. I've said standard engineering practices, standard engineering measurements. So I want to define what that term means. When I say standard or standard engineering or standard engineering conditions, I'm talking to a specific set of variables in our environment that have been set for purposes of communication. If we assume that an object is at sea level, then what would the atmospheric pressure be? And you can look it up, right? The atmospheric pressure is going to be 101.3 kilopascal. In English units, that would be 2,116 pounds per square feet. Notice that I wrote PSF as pounds per square feet. If we assume that our objects, our structures, are at sea level, then they will be experiencing an atmospheric pressure of 101.3 or 2,116, and we call that a standard value. There's another value for this. We call it 1 atmosphere, where 1 atmosphere simply refers to the amount of pressure at sea level. When it comes to temperatures, the standard engineering conditions for temperature are typically measured in relative scales. And they are 15 degrees Celsius, which is equal to about 59 degrees Fahrenheit. So when you hear me say an object is at standard engineering conditions, what I mean is that the atmospheric pressure is 101.3 or 2,116, depending on the unit system, and that the temperature is 15 degrees Celsius or 59 degrees Fahrenheit. So that's what we mean when we say standard engineering conditions. And this really helps to simplify our problems because it allows us to make assumptions of our problems. If we want to study the effects of buoyant force, but we want to look at absolute terms, then we can always assume standard engineering conditions. Now again, standard engineering conditions means conditions that we're going to have here on Earth. If we're doing aerodynamic applications where we're considering space shuttles or things moving at very, very high speeds, very far away from the Earth's center and not experiencing any atmospheric pressure, we cannot really say that those are standard engineering conditions. So you'll hear me say the term standard engineering conditions to refer to things that are, well, probably right here around us. Lastly, there is one more thing we need to learn before we start our formal study on fluids, and that is our approach to fluids. I want you to consider a blob of fluid. What is that blob made of? Well, you're going to say, well, a fluid. Well, no duh. But this fluid, let's say it's water, should be made of hydrogen and oxygen molecules, right? Many of them, thousands, millions. If we were to zoom in as much as possible, then we could, in theory, zoom in to a point where the distance between these molecules is actually too big, to the point where we can't really study properties such as its density, or we can't really determine the distribution of pressure forces. This study of fluids that focuses on fluids at a molecular level is what we call the statistical approach. Now, because this is an undergraduate course in fluids, and because we are focusing on engineering applications, we really won't follow the statistical approach for fluids. In fact, the statistical approach theory is really incomplete for dense gases and liquids. The statistical approach, where we study molecules, individual molecules and their movement, is actually a little bit better suited for gases, such as air around a shuttle that is entering Earth's orbit or entering the atmosphere. So we're not going to study fluids as individual molecules. What can we study fluids as? So if we look at a fluid and we instead see it as a continuous substance with no spaces in between, then we can study a fluid through what we call the continuum approach. So the continuum approach, or continuum mechanics, will assume that our substances are continuous, that there are no gaps in between their molecules, and that allows us to study properties such as pressures and densities in a fluid. In order for the continuum approach to be valid, we need to assume a couple of things. We need to assume that the free path between two molecules is so small compared to the length scale of the fluid that we are studying, that it will be basically negligible, and it will be okay to ignore that distance. That means that for standard engineering conditions, if we're studying water in a river, if we are studying oil in a pipe, the continuum approach is a good approach. But if we want to study fluids at the molecular level, we're going to have to head back to the statistical approach. So I hope that in this lesson, we kind of refresh a little bit of the terms, some of the terms that we're going to study throughout the semester. Keep in mind that this class will follow the continuum approach. It will not follow the statistical approach. You can learn more about statistical mechanics in upper level courses. So that's it for today. So on next week, we're going to start looking at some of the basic properties of fluids, its density, its specific weight, its viscosity. But for now, I would like for you to focus on these prerequisites, things that we need in order to study fluids.